All right, today we're going on a quest, but not for buried treasure. We're looking for something way more fundamental, the most direct, the most pure, the most unshakable path to logical truth.
Think about it like this. You're trying to get from point A to point B. You could take the scenic route, right? Full of weird turns, maybe you get a little lost. Or you could take the most direct path possible. In the world of logic and math, that's not just a simple question. It's actually a deeply profound one, and it leads us to one of the most beautiful ideas in all of modern thought.
So here's our game plan for this explainer. First, we'll dig into the problem with detours in logic. Then we'll meet our hero and his elegant solution. After that, we'll see the unbelievable power of purity his idea unlocks, how it creates this wild bridge from logic to computation, and then, finally, we're going to hit the twist, the price of perfection.
Okay, first up, the problem with detours. So before the 1930s, the world of mathematical proofs was, well, it was kind of messy. I mean, the proofs worked, but they often felt like these magical black boxes. You could see the end result was true, but the path to get there, it was a total mystery, a really winding road.
And this phrase, which is just incredible, really says it all. Proofs relied on fortuitous alien intermediate concepts. I mean, what does that even mean? It means a proof might just grab some brilliant but totally unrelated idea from a completely different field of math, like a clever trick, just to get over the finish line. It's like taking a magical portal that drops you at your destination, but you have no earthly idea how it connects to the road you started on.
Logicians have a name for these: synthetic proofs. They use all these external ideas, these lemmas and shortcuts. And look, they can be absolutely dazzlingly clever, but they are fundamentally indirect. And here's the big problem: they completely hide the essential structure of the argument. It's like looking at this beautiful machine, but you have no clue how the gears inside are actually turning. That makes it super hard to analyze the proof or, to be sure it's foundationally consistent.
And into this complicated world steps our protagonist, a German mathematician and logician named Gerhard Gentzen. He looked at all this mess and thought, there has to be a better way. There has to be a way to bring some order, some clarity to all this.
And his big breakthrough happened really fast, over just a few years. In the 1930s, he introduces this revolutionary new system he calls the sequent calculus. By 1934, he's publishing his work, and it all leads to this incredible theorem he called the Hauptsatz, which just means main theorem. But this wasn't just another paper. Oh no, this was a total game changer for the very foundations of mathematics. So what is this Hauptsatz? Well, it's also known as the Cut-Elimination theorem, and at its core, it's a precise recipe for systematically removing all those clever but unnecessary detours, which Gentzen called cuts, from any proof. And here's the magic trick: you can get rid of all of them without ever changing the final answer. It is literally a method for finding that pure, direct path we've been looking for. And this just shows the transformation perfectly. On the left, you've got a proof with a cut. It's synthetic, it's using outside ideas, and it hides the core logic. But on the right, after you apply Gentzen's theorem, boom, you get a cut-free proof. It's analytic. It builds step by step directly from what he started with, and, most importantly, it reveals the essential, beautiful structure of the argument. It's pure. Okay, so what? Why is this a big deal? What do we actually gain from having these super clean, direct proofs? Well, as it turns out, the consequences are absolutely massive. The first mind-blowing consequence is something called the subformula property. This is where the true power of purity really shines. It guarantees that every single step, every single formula in that clean, cut-free proof is already a piece of the original statement you were trying to prove. No alien concepts are allowed. The proof is totally self-contained. Everything you needed to get to the conclusion was already there, hiding inside the question. And having this property unlocks some unbelievably powerful tools for logicians. All of a sudden, they could rigorously prove the consistency of an entire logical system, making sure it could never prove something is both true and false. They could determine its decidability, which is basically figuring out if a question even has a provable answer. In short, Cut-Elimination became like a master key for analyzing the health and structure of entire systems of logic. And this wasn't just an abstract exercise. Gentzen himself used this exact method to do something monumental. He proved the consistency of elementary number theory. He was helping secure the very foundations that a huge chunk of modern math is built on. But the story doesn't end there in the world of pure logic. In fact, This is where things take a really fascinating, unexpected turn, and we jump from the world of proofs straight into the world of computation.
Because it turns out that the pure, direct structure Gentzen uncovered wasn't just describing logic, it was secretly describing computation itself. This profound link, which we now call the Curry-Howard correspondence, forms this beautiful, stunning bridge between the world of proofs and the world of computer programs.
It's like a three-step dance. Step 1, you can take a logical proof and translate it into a piece of code, something called a lambda term. Step 2, the process of eliminating a cut from that proof, well, that corresponds directly to Step 3, a computation step in the code. Think about that. Simplifying a proof is running a program. They are literally two sides of the same coin. This has led to this really cool modern field called proof mining. It's exactly what it sounds like. You take a complicated synthetic proof, you use cut-elimination to strip away all the shortcuts, and you extract hidden mathematical and computational information directly from its pure structure. We are literally mining old proofs for new knowledge. And that brings us to our final section, the price of perfection. Because this beautiful, direct, pure path to the truth, it comes with a jaw-dropping catch. So we have this perfect method, right? It reveals the very DNA of logic. It connects it to computation. What could possibly be the downside? What's the catch here? Well, here it is, a proof that uses a clever shortcut. A cut might be, say, 10 lines long, nice and short. But if you eliminate that cut to create the pure direct version, the resulting proof can explode in size. And I don't mean just get a little longer. We are talking about a non-elementary increase, a growth so fast it's basically unimaginable. That tidy 10-line proof could become so long that writing it down would require more atoms than exist in the entire observable universe. No exaggeration. And this reveals the great paradox of Gentzen's amazing work. While those cut-free proofs are theoretically perfect, those cuts, those detours, are practically essential. They're the powerful lemmas, the theorems that let human mathematicians build on each other's work and actually get things done. We need the shortcuts just to make progress. And you know, this paradox has created some really fascinating challenges in modern logic. A lot of newer logical systems don't even work without something like the cut rule. So to solve this, logicians have had to invent more complex frameworks, these new ways to manage and control shortcuts, all in an effort to get the best of both worlds without losing the powerful insights that Gentzen gave us. So in the end, Gentzen's Hauptsatz did something truly extraordinary. It peeled back all the layers of our arguments to reveal the fundamental DNA of logic itself. And in doing that, it uncovered this shocking, profound connection between the abstract act of proving something and the very concrete essence of computation. And that leaves us with one last big thought to chew on. If the purest, most direct, most fundamental path to truth can be, for all practical purposes, impossibly long, what does that tell us about our own, very human search for knowledge?